sklearnmetricspairwisemanhattandistances. Manhattan distances. Description. This function calculates the Manhattan distance between pairs of data points. The Manhattan distance is also known as the taxicab or L1 distance. It is calculated as the sum of the absolute differences between the corresponding coordinates of 2 points. Inputs. X a 2D array of data points with shape n samples 1. N features. Each row represents a data point, and each column represents a feature. Y a 2D array of data points with shape n samples 2. N features. Each row represents a data point, and each column represents a feature. If Y is not given, it will be set to X. Outputs. Distances. A 2D array of pairwise Manhattan distances between the data points in X and Y. It has shape n samples 1. N samples 2 if Y is given, and shape n samples 1. N samples 1 if Y is not given. Steps. It calculates the absolute difference between corresponding coordinates of each pair of data points. It sums the absolute differences across all features for each pair, resulting in the Manhattan distance. Metrics. Manhattan distance, the primary metric computed by this function. It represents the sum of absolute differences between corresponding coordinates. Visualization plots. Scatter plot, visualizing the data points in a scatter plot where the distance between points reflects the Manhattan distance, can provide insights into the distribution of the data and pair relationships between points. Heat map. A heat map of the pairwise Manhattan distances can help visualize the relationships between data points, with darker colors indicating closer distances. Fine-tune parameters. None. The function does not have any parameters for fine-tuning. Uncertainty methods. None. This function does not directly provide uncertainty measures. To estimate uncertainty, you might consider using bootstrapping or other resampling techniques. Challenges and fixes. Challenge 1. High dimensionality. When dealing with data in very high dimensions, the Manhattan distance can become less informative as it becomes more sensitive to small differences in individual features. Sample use case that resulted in challenge 1. Analyzing text data with a large number of unique words or features. Fixes to challenge 1. Feature selection. Reduce the dimensionality of the data by selecting the most relevant features. Dimensionality reduction. Apply techniques like principal component analysis (PCA) to project data into a lower dimensional space while preserving important variance. Challenge 2. Scale of features. The Manhattan distance is sensitive to the scale of features. If features have very different scales, the distance will be dominated by the feature with the largest scale. Sample use case that resulted in challenge 2. A dataset with features representing age, income, and number of purchasers, where the scales are significantly different. Fixes to challenge 2. Feature scaling. Apply standardization or normalization to ensure that features are on a comparable scale. Weighted Manhattan distance. Assign weights to each feature based on its relative importance to adjust the distance calculation.